Good morning, everyone, and welcome. I am pleased to have the opportunity to present today on a very important topic. The title of our presentation is Procedure for System Suitability Test in HPLC Analysis. Today, we will explore the key steps and considerations involved in ensuring our HPLC systems are suitable for accurate and reliable analysis. We'll cover the fundamental procedures, best practices, and some practical tips to help you implement this effectively in your work. Let's get started and dive into the details. Let's talk about the purpose of SST, or System Suitability Testing. Its main goal is to verify that our system is performing with the right level of precision and accuracy, ensuring that the results we get are reliable. It also helps us make sure that our system's performance is reproducible, meaning we can get consistent results across different runs. Additionally, SSD is crucial for detecting any system faults early on, so we can address issues before they affect our analysis. It confirms that our chosen method is suitable for the task at hand, giving us confidence in our process. As part of the introduction, it's important to remember that SSD is a key quality control step, especially when working with HPLC or high-performance liquid chromatography. SSD makes sure the system is performing optimally before we start our analysis, which is vital for obtaining valid data. In regulated environments like USB, ICH, and FDA, SSD isn't just recommended, it's mandatory. It needs to be conducted both before starting the analysis and periodically during the process. This ongoing check helps maintain the integrity and accuracy of our results throughout the analytical run. Let's start with system equilibration. It's essential to flush the system with the mobile phase to ensure everything is clean and ready for accurate results. After that, we run a few blank injections. These help us confirm there's no residual contamination affecting our analysis. We then equilibrate the system for about 10 to 20 column volumes, giving enough time for the column to stabilize. The key here is to ensure a stable baseline before proceeding, which indicates the system is in a good state for reliable data collection. Moving on to system preparation, it's crucial to use a calibrated HPLC system to maintain accuracy. Preparing fresh mobile phase that's both filtered and degassed helps prevent any particulates or gases from interfering with the analysis. Proper installation of the column is vital. Any misalignment can lead to inconsistent results. When setting your method parameters, make sure to specify the flow rate, wavelength, and injection volume precisely, as these directly influence your separation quality. Now let's talk about the key SSD parameters. Retention time, or TR, indicates how long a compound takes to pass through the system, which is fundamental for identification. Theoretical plates N measure the efficiency of your column. The higher, the better. The tailing factor, T, helps us understand peak symmetry. Ideally, peaks should be symmetrical for accurate quantitation. Resolution, RS, tells us how well two peaks are separated, crucial when analyzing complex mixtures. The percent RSD, or relative standard deviation, assesses precision. Lower values mean more reproducible results. Lastly, the capacity factor, K, provides insight into how well a compound is retained relative to the mobile phase, helping us optimize separation conditions overall. Connecting all these points, proper system equilibration and preparation are the foundation for obtaining accurate, reliable data. Monitoring key SSD parameters ensures your method performs consistently and helps you troubleshoot if results deviate. This process is central to achieving quality in your analytical work. Now, let's talk about the injection sequence. Typically, you'll want to inject your standard solution around 5 to 6 times. This helps ensure that your system is stable and that your results are reliable. After each injection, record the chromatograms carefully so you can monitor the peaks and make sure they remain consistent throughout the process. Consistency of peaks is crucial because it indicates that our method is precise and reproducible. Moving on to standard preparation, it all starts with accurately weighing your standard. Precision here is key to achieving accurate results later on. Once you've weighed the standard, prepare the solution according to your specified method. Remember to filter the solution through a 0.45 micron filter to remove any particulates that might interfere with the analysis. And whenever possible, always use a fresh solution for your experiments to maintain consistency and accuracy. By following these steps diligently, we ensure that our calibration and analysis are both accurate and reproducible, which ultimately supports the reliability of our entire analytical process. Let's walk through a typical QC sequence. First, we start with a blank run, which helps us ensure that the system is clean and ready. Sometimes we include an optional blank for confirmation. This extra step can help verify that everything is in order before moving forward. Next, we run our standard samples 5 or 6 times, which are used for the SSD evaluation to check the system's consistency and accuracy. Then we analyze our samples, starting with sample 1, followed by sample 2 and sample 3. After that, we run a standard in a bracketing position around our samples to ensure the measurements stay within acceptable limits. We continue analyzing additional samples as needed, following the same pattern. All of this is part of our injection program, which is designed to maintain precision and reliability throughout the process. By following this sequence, we ensure our data is accurate and reproducible, which is essential for high-quality results in any analytical setting. Let's take a closer look at the concept of theoretical plates, represented by the symbol N now. This might sound a bit abstract at first, but it's actually a really useful way to understand how effective a separation process is. Essentially, each theoretical plate can be thought of as a hypothetical stage where the solute equilibrates between the mobile and stationary phases. The more plates we have, the more times the mixture is effectively, repeatedly refined, leading to better separation. The key point here is that the number of theoretical plates, N, is directly related to the efficiency of our column. A higher N indicates a more efficient separation, meaning our components are more distinctly separated with less overlap. This is crucial for achieving pure, well-defined products, especially in complex mixtures. Connecting this to the overall theme, understanding and optimizing N helps us improve our chromatography process, whether we're aiming for sharper peaks, better resolution, or faster analysis times. So, by focusing on the number of theoretical plates, we're essentially honing our ability to produce cleaner, more accurate separations in our work. Let's take a closer look at resolution, measured in RS. Now, resolution essentially reflects the level of detail or clarity in an image or a system. Higher resolution means more detail, which can be crucial depending on the application's requirements. When we talk about RS, we're referring to the specific monetary measurement, but in this context, it also symbolizes the precision or quality level we aim for. Understanding resolution is key because it impacts everything from the quality of visual outputs to the accuracy of data. For example, in imaging, a higher resolution provides sharper, more detailed pictures. In other systems, it might relate to the finer granularity of information. So, as we move forward in this presentation, keep in mind how resolution directly influences performance, quality, and ultimately the value we get from our systems. It's a fundamental concept that ties into the overall theme of optimizing efficiency and output. Now, let's take a closer look at troubleshooting SSD failures, focusing on the acceptance criteria summary. When we're dealing with SSD failures, it's essential to remember that having clear acceptance criteria helps us diagnose and resolve issues more effectively. These criteria act as a benchmark, allowing us to determine whether a system is functioning as expected or if there's a failure that needs addressing. Throughout this process, the key points include understanding what conditions must be met for a successful SSD operation, recognizing common failure points, and knowing how to verify each criterion during troubleshooting. By doing so, we ensure that our troubleshooting efforts are thorough and targeted, saving time and reducing errors. Connecting this to the overall theme of ensuring system reliability, having well-defined acceptance criteria helps us maintain high standards and quickly identify deviations. This approach ultimately supports smoother operations and more resilient systems. Remember, clear criteria are the foundation of effective troubleshooting, and continuous improvement. Let's go over some common mistakes to avoid in our process. First, skipping blank injection can lead to inaccuracies, so always remember to include that step. Using insufficient standard replicates is another pitfall. Having enough replicates ensures reliability and confidence in your results. Ignoring failing SSD results can be tempting, but it's crucial to address any issues before proceeding. Injecting samples before getting SSD approval is a big no-no. Always wait for the green light to avoid compromising your data. Now, moving to some practical tips. Always run a blank before the standard. It helps prevent false positives and keeps your analysis clean. Never inject samples before your SSD has passed. This ensures your system is ready and working correctly. Use fresh standard solutions for each run to maintain accuracy. Consistency is key, so maintain a uniform injection volume across all samples and standards. Lastly, if you're working with long sequences, use bracketing standards. They help correct for any drift over time, keeping your results accurate throughout the run. Following these points will help you avoid mistakes and ensure high-quality, reliable data. Let's take a moment to summarize the key points we've discussed. First, the blank check is used to verify cleanliness, ensuring that there are no contaminants that could affect our results. Next, the standard serves as proof of the system's performance through the System Suitability Test, or SSD. Only after the SSD passes do we proceed to the actual analysis, which is the test phase. The main takeaway here is that the SSD is crucial for maintaining reliable HPLC performance. It's not just a formality. It's vital for ensuring data integrity and compliance with regulatory standards. Regular monitoring of the SSD helps prevent analytical errors before they occur, making it an essential step in pharmaceutical analysis. In essence, consistent SSD checks keep our system performing optimally and our data trustworthy. For further support, please don't hesitate to reach out. If you have any questions or need additional information, I'm here to help. You can contact us through the provided channels. And with that, I want to thank you all for your time and attention today. I appreciate your interest and engagement with this presentation. Thank you again, and I look forward to connecting with you soon.